Hi, I'm going to introduce Jessica. Is a technology agnostic by choice, I think is what you call yourself. Is that right? But by career. No, well, I hope you chose your career. And Jessica's going to talk about something about pipelines in AWS, I believe. But I'm going to leave that to you. So welcome, Jessica.
Hi, my name is Jessica Flanagan, and I'm here to present Working with Large Numbers of Non-Trivial ETL Pipelines, or how I've stuffed it up so you don't have to. This talk is based on my experiences building a data pipeline system at Datadog Technologies. At Datadog, we work with US city and county governments to provide actionable insight into their data. We combine public and private US national and municipal data sources to detect patterns of interest and discover anomalies. We clean, process and merge these data sets so that we can use machine learning to see the data in a way unavailable to our customers. We're a fairly new company and we got our initial MVP running in just 3 weeks and had to continue delivering from there. Starting from scratch and at speed has meant we've designed our systems using the latest tools and practices, but we've also made a number of mistakes along the way. I'm here to present our pipeline architecture and highlight some of the lessons learned. I'll be talking a lot about AWS and Datadog, and most of it good. However, I'm not sponsored by either, and the core concepts of what I present could be easily ported to a different cloud provider and on an elk stack. First, I'll show you our business model and how it translates into our pipeline architecture. Initially, we gathered data from a variety of esoteric formats such as GIS shapes, scanned PDFs, database dumps, Excel files, and we used that to generate actionable insight.
So we ingest all of that different data and we give them actionable insights that they can do with that data. But we wouldn't be a modern venture capital-backed startup if we didn't have data science. So we take esoteric data, apply data science, get data insight. But as many of the people in this room may have discovered, data scientists can be quite lazy. And they do not want to create a different data model for every city within every county for every different data type. So we take the data, we create a semi-relational data model, then we apply data science, and then we get insight. And so today, I'm going to talk about the first stage of that. So we go from our data to the minimal amount of changes required to get that data into our data lake to our semi-relational model, and that's what I'll be talking about. So the problem space for this talk. What is a non-trivial ETL pipeline? Well, if you're just going to stick something in an S3 bucket and trigger a Lambda, you don't need a pipelining tool. You're just adding overhead. So in this case, we're going to talk about things where there's branching and steps and things can fail anywhere along the way. And what is a large number of pipelines? Well, it's anything beyond what you're going to be willing to watch every day. I've worked on big projects where we built one giant data pipeline for emulating a self-driving car. I didn't need to monitor that. If it failed, a senior VP would be on the phone yelling at us. So no monitoring was required. We had a system. And then there's other data pipeline systems where you have a lot of data pipelines, but the only person who cares whether that data pipeline succeeded is the person who wrote it and the person who's running it. And in which case, all you need to do in that sort of scenario is protect the users from each other. So this is the scenario where we create a lot of data pipelines and the people who need them are not necessarily the people who wrote them. So the architecture goals I'm trying to achieve is we want data pipelines that are easy to debug, and when they fail, we want to be able to see what stage they failed and any related logging. We need a whole system view. So when someone says, can we produce a report for Riverside County or for the state of California, I want to be able to see all of my data pipelines and see that they've been happily running. We need monitoring so that if the data pipeline is getting worse over time. It's not enough to say that my data pipeline started, it ran, it was happy. I want to see if I'm getting less and less data. Anyone can mess up our system. For example, they decide to start using a worse scanner for OCRing their documents, and we start getting more null records. So we want to see over time how things are performing. And finally, if the data pipeline fails, we want to know exactly who's going to fix it, because just having errors announced is like yelling, help into a crowded room. No one knows what they're supposed to be doing. So we need to target an individual person to help us. So back to our architecture. So this is a very traditional type of architecture that you've probably seen before. This is our extract stage, our transform, and then we load it into our relational model. And I'm going to talk to you about how we've implemented that on Amazon to give you sort of some context. Whenever possible, always show you're working. So you'll notice we've got the extract, transform, and load stage. We give our data scientists and our data engineers access to every one of those stages, and we make it very easy to do. So you can see where the data came from and what it looked like. So our extract stage, we either run a Docker container, I know it's a dirty word, or an Amazon Lambda. The reason why we sometimes run Docker in batch is because when we started in June last year, Lambdas were limited to 5 minutes, and you can't rely on county servers to give you data within 5 minutes in some scenarios. Because some of them will not just give you an update of this week's data, they will give you the last 20 years of data every time you talk to them. So in those scenarios, we have to run a batch job. Everything else we run Lambda. And then we dump it into an S3 bucket in completely raw form. If they give us a zip file, we dump it as a zip file. We do nothing to it except store it. After that, we do our transform stage. Once again, it's either Lambda or batch. It's batch in the scenario where we've got to do a long job, like extracting GIS features. We might run it in batch. Everything else will run in Lambda. And then we stick the now what we call structured data into S3. So this is generally either CSV or JSON, or in the case where we've got a PDF where we've annotated, it's the OCR version, or in cases of images, all we're doing is dumping the metadata related to those images into S3. After that, we either run a glue crawler or a Lambda job to load the petitions. And we do that so that we can put this data into our data catalog. And then that means we can access the data via Amazon Athena. Amazon Athena is a Presto implementation that lets us to now view that data using a subset of SQL queries. So once we've done that, any of this data we've got here that's been semi-transformed is available via S3. And then finally, our load stage. This is where we run AWS Glue. AWS Glue is an on-demand Spark cluster. And so that's where we align our data. That's one of our biggest jobs, is aligning what pieces of data belong together. Because, for example, for one piece of land, it is described differently from by the homeowner, by the county records, by our GIS engineer, and by an accountant. And so we need to work out who's talking about what and whether they're talking about the same thing. And we do all that via Spark, PySpark scripts that we run on AWS Glue. And then once again, we stick that into our data catalog. And the output of our Glue job is a Parquet file, which is a columnar data format that we partition by things like zip. So that means it's speedy for us to access individual columns of that data, but also by partitioning it into sort of regional areas, it's quick for us to access by groupings. And so that's our basic pipeline that we use over and over again. One of the other mistakes we made, because this is a lessons learned talk, is when we first started, we stuck everything in the same S3 bucket. Extract, transform, and load. We just had a data bucket. We have completely different backup and access requirements for all of those stages, and that made life difficult. I honestly generally don't care if we lose our transform stage or our load stage, because all of it can be regenerated. The thing we do care about is our extract. Even if we can get that back, we can't know what it looked like in May, 2018. So split those up. We fixed that, but that was a mistake early on. Once we decided we wanted a data pipelining tool, there is no shortage of data pipelining tools you can choose. This is nowhere near all of them. This is just a subset of some of the examples. But I break them in my mind into data specific or flexible. And data specific are ones that give you a lot of easy tools for doing SQL style transformations. Whereas flexible ones are where I just want to run functions one after another, and they could be anything. So because of the type of manipulations we're doing, like OCRing, we wanted a flexible one, and since we were already so far in AWS, we went with step functions because it makes it easier for us to trigger things like our lambdas without having to write overhead. So that was our choice. I've used Apache Airflow before, and it's great, but it has a lot of resources dedicated to not overloading things, and I just don't care. That's Amazon's problem. So step function. This looks very complicated, but I'm going to drop it down very quickly. The most important part is it's a flow diagram. So it allows us to define what we want to do and how we want to react as things succeed or fail. And it can be broken down into tasks. So these are our Lambda tasks, so things like running the Athena rebuild, checking to see if that's finished. We can run batch jobs. That's how we can trigger our glue jobs. So any of these are defined as tasks, and we have an input and an output. We also can process the results of tasks, so these are called pass states. So they take the output and format it in the way that is expected by the next state. We have waits, so things like our Athena rebuild, which is where we load our data catalog, can take up to 30 minutes. So we write a Lambda function that starts that process, and then we poll to see if it's finished. So we can have a wait state so that we're not running a Lambda the entire time. Finally, we've got these choice states, so we look at the output of the previous steps and we decide what to run next. And then we can mark the jobs as success or failure. So those are sort of the key features of what we can run in step function and what comes out of the box. This is an example of one of our step functions running. So it starts by running the batch job. What's happening right now is always marked in blue. If it succeeds, it becomes green. So then we run the Athena rebuild. We wait for a while. We check to see if it's done. If it's not done, we wait again. Now it is done. We can run our glue job and mark as success and then report the result. And so as you can see, as my step function runs, I can see exactly what it's doing. And if it failed, there'd be a big red box on where it got to. So I've now got a way to see what's happening for each individual step function. One of the key advantages of step functions is that they can be written very generically. So the tasks describe what they're going to do, but they do all of that. They can do all of that based on input. So your step function, when you define your step function, you define a series of states, but you also, every time you run it, you give it a JSON input, and that determines what it's actually going to do. So for each individual task, it looks at the overall input, examines its input path, and uses it to fetch its parameters out to give to whatever AWS service it's going to run. So be that Lambda or Glue or Batch. It outputs the result of that stage into the result path, and that becomes part of the global state of the step function. So what this means is we can write one step function and then define exactly how it's going to work using the input. So on the left-hand side, I've got a step function definition, and on the right-hand side, I've got a job input. So on the right-hand side, I can specify what my job name is going to be, and that gets fed straight into my task. So this is for a batch job. I've got my batch job queue, so that's where I'm going to actually run this. I've got my job definition, so this is my Docker image that I'll be running. And then I've got a blob of logging that I give as an environment variable that I'll go into in a little while. And finally, I can override the default command. So this one left-hand side task definition at no point knows anything about what it's actually going to run. It's very generic. And that saved us a lot of time. When we first started creating pipelines, we would define as part of our project our step function definition. And then when we changed how we wanted to do error handling or reporting at the end of the step functions, we'd have to go into every pipeline and go and update how they work. And that was a maintenance nightmare. In the end, we've ended up with about 6 pipeline definitions, and they cover almost all of our use cases. There's only some very small examples where we have to write custom ones. So if you can, reuse them. So this is our sort of CloudFormation stack. So in our base stack is where we define our step functions, our IAM roles, our batch environment, our glue config, our shared lambdas, our SNSQ. All of that is defined in one place, and that makes it easy to maintain. When we write an individual pipeline, all we mostly need to define is the actual scripts of code that we're going to run in that environment and some data definition language for how we want to access that data. So our batch job here is just our Python code that's going to run on batch. There should be a Lambda thing there, but it's not there. Details about our glue job, that's just our PySpark script, and as well as our Athena data definition language, and how or when are we going to trigger this job. So we trigger our pipeline jobs using CloudWatch Events, and in that trigger, we give it a step function arm, so that's which of our generic step functions we want to run, and the JSON input that we want to give to that step function that tells it what we actually want it to do. That triggers our start step function Lambda, which is something we've created, and that starts up the step function, and it also initializes the logging environment which we use. And finally, that runs the step function. And so that's how our pipelines get started. So onto the logging that we've kind of hinted at a few times. So our logs are now everywhere. We've got logs from all the various Lambda functions, and they're all sharing the same Lambda functions, so those logs are all intermixed. We've got logs from our batch jobs, which are all going into their own CloudWatch stream. We've got glue logs, which are very verbose, that are all getting piled somewhere. So if you want to work out, like when you see what has failed in our task, you've got to go work out which log stream it's in, and then you've got to dig all the way in. And then perhaps it's because something wasn't expected previously, so you've got to go dig further. So this was a big problem. It was very hard to work out what was happening with a pipeline. I came up, and I will say this was in a sleep-deprived state while trying to get an MVP out, was that we can just use logging handlers. Almost everything we write is Python. We can override the logging handler. We can redirect the logs to our own CloudWatch stream. It'll all be in one place. Life will be great. This was a nightmare. Now no longer does the AWS console work the way you expect it to do. You can't work with AWS support because nothing's where they expect. There's links to where logs should be and they don't work. Never do this. This is a terrible idea. Instead, what you should do, or what I felt we decided to do, was use JSON logging. So we still let the logs go wherever they want to go, but we tag that we create JSON objects for all of them. And then with all of those logs, we include additional logging fields than the normal Python ones. So we know what step function was running, we know which pipeline it's for, we know what county, because our customers are broken up into cities and counties, we know what county it's for, what city it's for, what type of data, and when it ran. And so we tag every one of our logs like that. So whether it's in Glue, Batch, Lambda, even in our batch ones, we've got small shell scripts for starting our jobs. We found a project called Bash Banyan, and we extended it so that we could add our own custom log fields. So everything we log is now in JSON. What that meant is we could then pipe almost all of our logs, or all of our logs in a lot of cases, straight into Datadog. Then we use Datadog to organize those logs based on those JSON fields. So all of those JSON fields I added can be used as facets to sort. So we can now look at the logs throughout the entire system for a job by picking the relevant facets. So we can search by county or by pipeline or whatever. We chose Datadog. You could use Logstash or anything else. But the key point was make the logs into something that's easy to process and then centralize them. After that, so now we can diagnose what's going on, but we need a quick way to tell whether our data pipelines are running. We're sharing all these step functions, we can see they're running, but we don't know if we're running data for a specific customer and whether it's happening at the right sort of timeframes or if someone's turned something off. So to deal with that, we use Datadog checks, which is sort of traditionally sort of like what you would use for a CPU check or a memory load check. So if a pipeline completes, we send an OK check. If a pipeline fails, we send a critical check. I moved over our newer stuff to this when we started doing this, and it was great. I could generate dashboards where I could see all of our pipelines on one page. And then I went to move some of our original code. And that's when I discovered this completely undocumented feature of Datadog, which is a check is considered inactive if it's not updated after 24 hours. Some of our jobs run monthly, so that quickly became a problem. They just disappeared. I did get confirmation from Datadog support that this is true. They may have updated the documentation now, but it wasn't the case earlier. So what we use instead for those is Datadog Events. So they get stored for months rather than hours. And the end of all of our step functions, we have that custom report step function Lambda, and it will submit an event type of error if our job fails, an event type of success if it ran successfully, and another important one is an event type of warning if we ran but we produced no data. Sometimes that's okay. Sometimes we're polling a county and we fetch and we get the same file, but that shouldn't happen too many times in a row. And these are all, we tag everything with the same fields we use for JSON logging, so we use those consistently through. This lets us create a different type of dashboard where we generate custom Datadog alerts based on those events, and then we can display those. Now, we also want to monitor metrics. We want to know how well our jobs are performing. So are we getting less data or more null records or more missing? But we don't want to just do that from the report step. It's kind of hard to pull out outside. So we want any of our code to be able to do that without understanding Datadog too much. So we did that by creating an SNS queue. And any part of our process can generate a blob of JSON that describes a metric, shove it on SNS, and then we've got a Lambda that watches that queue and will pass it to Datadog. So now our glue job, our Lambda functions, any of those can report how we're going. And that lets us generate dashboards automatically for any of our pipelines that show how they're performing over time. So alerting. So there is an alert task within the step function definition. A SNS task within the step function definition. We tried using it. It wasn't very practical. It only allows you to give it one chunk of that JSON object and shove it on an SNS queue. We wanted to be able to put together what pipeline it was, when it happened, and build a string. So instead, we had to write our own Lambda for that. But then shoving alerts straight onto Slack meant that people got alert fatigue. Every time a pipeline failed, even if someone was rerunning it to deal with a failure, we'd get more alerts. So it just became ignored and annoying. So instead, we let Datadog manage our alerting. The advantage of this is that once a pipeline falls into an alerting state, it doesn't keep alerting you again and again. It will only alert the first time, or if you set up some type of escalation. And then using an integration for Datadog, we hook that into our Jira system. So now when an alert occurs, it generates a ticket and assigns it to someone. So then someone knows whose job it is to deal with it. We still update Slack, but now it's a lot less noisy. And you can set up custom alerts in Datadog. This is what you do when you're dealing with checks. So you can set how many warning states are okay versus failures. And it all can be done via an API. So we're not actually using this UI. I often use it just to figure out the features. Because I'm a big believer in infrastructure as code because it's sort of the standard now. So rather than define our alerts and Datadog dashboards in Datadog, what we do is we write a JSON blob and we include it in our source code repository. We've then written our own custom CloudFormation lambdas, so when we deploy our stack, it also deploys our Datadog dashboards and alerts using our custom lambda. So then that's all managed in the same space and it's all kept in sync. So back to our architecture goals. We wanted to create pipelines that were easy to debug, and when they failed, we wanted to see where that occurred. So we achieved that with step functions and using JSON logging with Datadog. We wanted a whole system view, so we could see whether we were delivering everything we needed for a customer, whether we could run further reports down the trail, and we achieved that using custom dashboards. We wanted monitoring, so we could see if our pipelines are degrading over time, and we did that with Datadog metrics. And we wanted a way to make sure that if our pipelines fail, someone is actually tasked with the job of fixing them. And so, in summary, log everything with JSON. If you think you can't log it with JSON, you can probably find a way. Where possible, share your step functions because you'll otherwise create an updating nightmare. Use the same tags for everything. Tag your resources, tag your CloudFormation resources, tag your logging, tag your events, everything with those same sets because it will make life so much easier to keep track of things and group them. Using custom CloudFormation resources, so we did that for our Datadog checks, but I think there's a lot of other places you could apply it. And don't move where logging goes. It is a terrible idea.
Very good. Thanks, Jess. Datadog. Alrighty. So, any questions at all? Oh, she's walking off. No. Sorry, I threw that one on you. Oh, we just got 5 minutes. If anyone had any, because there was a lot of information there, right? There's a lot going on. No?